And we're back. Today we're going to talk about solution stoichiometry, which is very similar to what we did last unit on stoichiometry. Now obviously we're just using it for solutions. And for these types of problems, normally for any solution you'll be given the molarity, the concentration, moles over liters, and the volume. And from that you can get the moles of your solution. And then from that point, the process is very similar to what we did last unit. In addition, we need to make sure what reaction is actually occurring. So first, we need to identify the species present. Then identify the species present. Then write the balanced net ionic equation. Now, before we do that, we first must write the completely balanced formula equation, the complete molecular equation, and then from that we can derive the complete ionic equation, and then from that the net ionic equation. So once then we have the equation, we can get the net ionic equation. We can calculate the moles of reactants, which I just said, remember, is molarity, the moles over liters times the volume in liters, and from that you get your number of moles. Then once you have the moles of each reactant, you can determine which one is the limiting reactant by converting to the mass of the product as your final step. Okay, so let's say here we have the following problem. We want to calculate the mass of sodium chloride that must be added to 1.5 liters of 0.1 molar silver nitrate solution to precipitate all the Ag plus ions Okay, so that means first step, we have to identify the reaction, what ions are present. So we know we are reacting NaCl with AgNO3. So those are our two reactants, and both of which, if you check the solubility rules, are both soluble, so they are both aqueous. And now we know with this double replacement reaction, our two products of this double replacement reaction, this sodium will replace the silver. So we have the Na plus ion, the sodium ion, reacting with the nitrate ion, and we get NaNO3. And according to your solubility rules, if NO3 is present, it is soluble, so it is aqueous. And then the silver reacts with the chloride ion to produce AgCl, which, looking at your solubility rules, is insoluble. Silver is one of the exceptions, so that creates a solid precipitate. Okay, and if we look, this reaction is already balanced. And now we can go on and write the net ionic equation. And for writing the net ionic equation, remember everything that's aqueous breaks apart. Everything that's solid remains together. So we know for our net ionic equation, the one product will be our precipitate, will be our solid. So that is AgCl. And a trick for writing the net ionic equation without having to write the complete ionic equation is if you look at the solid product, the precipitate, the two ions that are in that solid product will combine to form that. So AgCl comes from the silver ion, the Ag ion, as well as the chloride ion, both of which are aqueous. Okay, so now that we have the correct net ionic equation, and still that is already balanced, now we can do our calculation. So we know we had 1.5 liters of 0.1 molar AgCl, AgNO3. So we multiply those together to get so it's 1.5 liters of 0.1 molar. So from that we can get our number of moles of AgNO3. So that's our number of moles of AgNO3. And from that, we can get our moles of silver ions. If you look at the chemical formula, in AgNO3, in that compound, there's one silver ion. So for every 1 mole of AgNO3, there is 1 mole of silver ions. So that number of moles remains the same. So now we know the anion that precipitates the silver cation is Cl-. So if you look back at your balanced net ionic equation, for every 1 mole of silver, that was the coefficient in front of silver, there is 1 mole of the chloride ion. So that number of moles remains the same. And then now from that, we convert our moles of Cl- of the chloride ion to grams of NaCl. And same thing here, we look at the molecular formula of NaCl, sodium chloride. And in NaCl, there's 1 mole, there's 1 chloride anion. So that's a 1-to-1 ratio. And then last step, now that we have the moles of NaCl, now we can multiply by the molar mass of sodium chloride, which is 58.44. So our final answer here for the number of grams present of NaCl that's needed to react is 8.77 grams. So this process is the same for any stoichiometry problem using solutions. You have to identify the species present, then write the overall balanced molecular equation. Then from that, you can write the balanced net ionic equation. And then you have the volume and the concentration of each of the reactants. And from that, get the moles of the reactants. Then use those to convert to the mass of your precipitate, the mass of your solid product. And then identify which one is the limiting reactant, which one produces less of the solid product. And then you make sure that you check your answer to make sure it makes sense, and make sure all of your units match up. Okay, so we're going to go through a couple-step problem, because not only will you be asked for the mass of the product, but you will also be asked what, for different ions, what are the resulting concentrations of those different ions after a reaction occurs. Okay, so we have the following reaction. 10 milliliters of 0.3 molar sodium phosphate reacts with 20 milliliters of 0.2 lead nitrate. And you're assuming no volume change, meaning you're starting with 10 and 20 milliliters. You're assuming they're combining, so your overall volume of solution is 30, even though you know it will slightly change as you're producing that solid precipitate. So before we do any sort of calculation, we have to determine, okay, what ions are going to be present. So we have to write a reaction. So we know sodium phosphate, so Na plus and PO4 3 minus. So that will be Na3PO4, and that is soluble according to your solubility rules. Then lead 2 nitrate, so that's Pb2 plus and NO3 minus. So PbNO3 2, and that is also soluble. So now if we look at our products, the sodium replaces the lead. So now the sodium, the Na plus ion, goes with the NO3 ion. So NaNO3, which according to your solubility rules is soluble, so it's aqueous. And the lead replaces the sodium. So the lead ion, Pb2 plus, is reacting with the phosphate ion, PO4 3 minus. So we get a product of Pb3 4 2, which is insoluble according to your solubility rules. So that is your solid product. So that will be the precipitate that forms lead 2 phosphate. So now we have to make sure our equation is balanced. So if you look on the left side, we have 3 sodium ions. So you would think, okay, we put a 3 in front of the NaNO3. Except if you look at the next one, on the left side there's 1 PO4 ion. On the right side there's 2 of them. So therefore we have to put a 2 in front of sodium phosphate, meaning now there are 6 sodium ions on the left side, so we have to make sure there are 6 on the right. So now there's 6 nitrate ions on the right, so we add a 3 in front of the lead nitrate on the left side, and now everything is balanced, and from that we can write our net ionic equation. So we know with our net ionic equation, we write our solid product, the precipitate, on the right side, and we know the 2 ions that make up lead 2 phosphate are lead 2 plus and the phosphate ion. And we need to make sure this is balanced, so on the right side there's 3 leads, on the right side there's 2 phosphates, so we add a 2 in front of the phosphate. So now this is our net ionic equation. So now that we have that balanced equation, now we can determine the mass of the precipitate. So for each one of our reactants, we have the volume and the concentration. So we need to make sure we multiply the volume in liters. So we have 10 milliliters of 0.3 molar sodium phosphate. So that becomes 0.0100 liters times the concentration. So that means we have 0.003 moles of sodium phosphate. Oops. And we can do the same thing for the other reactant. We have 20 milliliters of 0.2 molar lead nitrate, so that 20 milliliters becomes 0.02 liters. So we have 0.004 moles of lead nitrate. Okay, so now that we have the moles of each reactant, now for each one we can convert to the mass of the precipitate, the mass of the solid product, to see which one is the limiting reactant. So for the sodium phosphate, we just said we had 0.003 moles of sodium phosphate. And so we can use the mole ratio from our molecular equation. Realize that ratio for every 2 moles of sodium phosphate, there is 1 mole of the solid product, lead 2 phosphate. And then last step, we multiply by the molar mass of lead phosphate, which turns out to be 811.54 grams per mole. So now, if we're using sodium phosphate, we would produce 1.2 grams of lead phosphate. Do the same thing for the other reactant. So we have 0.004 moles of lead nitrate. And same thing, we use the mole ratio from the balanced equation. For every 3 moles of lead nitrate, there's 1 mole of the solid product. And we convert to the mass of lead phosphate. So same thing, multiply by the molar mass of lead phosphate. For this one, we get a mass of 1.11 grams of lead phosphate. So therefore, since this mass is lower, that means lead nitrate is the limiting reactant, and the sodium phosphate is the excess reactant. So that means the mass precipitate that will form this reaction is 1.1 grams. So obviously that's a several step problem, so you need to figure out how we get there. So for pretty much any problem, you need to make sure you know which ions are present, write the full molecular equation, then write the net ion equation, then start the quantitative portion, make sure you know what the moles of each reactant are, convert that to the mass of product, and from there, whichever one is smaller, you can figure out which one is the limiting reactant. So also with these sorts of problems, you might be asked, what is the concentration of different ions after the reaction has completed? So here it's asking what is the concentration of nitrate ions left in the solution after the reaction is complete. So you have to think about if it's asking about a specific ion, if it is a spectator ion, or if it's not a spectator ion. So the nitrate ion, the NO3 minus ion, is not in your net ionic equation. So it's a spectator ion. So that means it's not used up during the course of the reaction. So that means we can use the amount of nitrate we started with to calculate this. So we know we started with 0.004 moles of lead nitrate, and we need to get the number of nitrate ions present. So in PbNO3 for every 1 mole of that, there are 2 nitrate ions. So that means at the start and end of our reaction, we have 0.008 moles of nitrate ions. So that's our amount of nitrate ions. And we want to know the concentration, or the molarity. And we know molarity, the concentration, is moles over total liters of solution. And we know we start with 10 milliliters and add 20 milliliters. So we have to make sure we add those two volumes together. Remember, we said there is no volume change, so we are assuming that that is the final volume. So 30 milliliters or 0.03 liters. Once you get that, divide that out, and you get a final molarity or concentration of nitrate ions of 0.27 molar. Okay. And now it's asking you about the concentration of a ion that is not a spectator ion. So it's asking you for the concentration of phosphate ions. So the phosphate is in the net ionic charge. So it is used up during the reaction. So what we can do, much like we did for the limiting reactant problems, we have to figure out how much product is left over from that excess reagent, because phosphate is present in sodium phosphate, the reactant, and it is the excess reactant. So we know, using that excess reactant, we would have ended up with 1.2 grams of lead phosphate, and our limiting reactant produced 1.1 grams of lead phosphate. So that means there's 0.1 grams of lead phosphate left over. So from that, we can calculate the moles of phosphate that are left over. Okay, so it's the reverse of what we did before. Now we're dividing by the molar mass of lead phosphate, and then converting to the number of moles of sodium phosphate used from the balanced chemical equation. If you look back at those coefficients, for every 1 mole of lead phosphate, there's 2 moles of sodium phosphate. So now what we get here, we get 0.0003, 3 times 10 to the 4th, moles of sodium phosphate. And now we have to look at the number of moles of phosphate ions. So in sodium phosphate, in 1 mole of sodium phosphate, there's 1 phosphate ion. So that number of phosphate ions remains the same, 0.0003. Okay, so that means that's the number of moles of phosphate we have left. And now last step, we just need to calculate the concentration, the molarity. So the moles, which we just said was 0.0003 moles of phosphate, and then over the total volume of solution, once again, which 10 milliliters plus 20 milliliters, 30 milliliters, or 0.030 liters. So we get a final concentration, phosphate ions, of 0.01 molar. Okay, so for each one of these, when calculating the concentration of ions, we have to think about, okay, is it a spectator or not? So for the one where we had to calculate the nitrate ions left over, the moles of nitrate present at the beginning is the same at the end, and then you just have to divide by the total volume. But for the one we just did, for phosphate ions, we have to think about how much are present at the start, how much are present at the end, get the difference there, the number of moles left over, and then divide by the total volume. So for all these reactions, before you start doing the quantitative portion, you need to make sure you write out the correct balanced equation, the molecular equation, and then you can write the net ionic equation. All right, that's all for today. See you next time.